Hi, everyone. It's me, Carolyn, and we are currently working in Chapter 3, and we've already looked at the measures of center, and so now we're going to move on to our measures of spread. What we mean by that is we want to know how tightly compact or how spread out our data is. So some measurements that we use to calculate those. And so I'm going to turn over to my guided notes, and we will go from there. See if I can get them to show up. There they are. All right, so this is section 3.2 in our textbook that we are currently using. And the first measure of spread is something we call range. And the range, or to calculate the range, we just simply take our largest value and subtract off our smallest value. And then I do have a question. I'll be like, is this measure resistant? Now, I want to remind us what resistant means. It means if we have an outlier, something incredibly large or incredibly small, if that's going to affect our measurement. And in this case, well, since we take our largest value minus our smallest value, if we have a really large value, yes, this is going to affect it. So this guy is not resistant. So any large or small values will change that amount dramatically. I'll come back and do an example in a second after we explain the next variables or next measurements as well. I do want to mention we do not have a symbol or letter that we use for range. It is used a very little bit. Most of the time people will use it in a sentence, like they'll say the data ranges from this value to that value. But I want to remind you that when we are using to find the range, we will actually take the largest value and subtract off the smallest value. And then we can say it ranged 10 units or 15 units or whatever that happened to be. The more sophisticated measures of spread is one that we have to get through by going through another value. The one we use most often is something we call the standard deviation. But in order to get to this standard deviation, we have to go through the variance. All right, and we do have our formulas here. And again, we have some funny looking symbols. So I'm going to take a little bit of time and tell you what these letters or symbols are. So this little guy here, like a little circle with a little flag on it, he is squared. So it is another Greek letter, and it is the lowercase sigma. So we will say that this is sigma squared. Okay, because he is to that second power. The squared part does come from the square that's inside that formula. So again, this is sigma squared. It is our population variance, which is different than our sample variance. We do use Greek letters when we are talking about our population. And we do have a slightly different formula. If you remember when we did the mean, the formulas were almost identical, except we were using a capital N versus a little n. But here we'll see even a little bit different, completely different bottom. So the way we find it is we can take the sum. So this guy, again, remembers is our capital sigma. And it means to add up. So we are going to be adding up a bunch of xi, that was our data value. And you'll see me, we're going to actually go through one of these by hand, just so you can get a feel for the formula itself. And by doing so, that way we can get an understanding of what the formula is kind of doing for us. And then we're going to subtract off this mu. So I'll remind you, this is mu, which is our population mean. We'll take those values We'll square them, and then we're going to add them all up. Once we get that value, we will divide by n, which is our population size. Okay. Here we have s squared. It is just s, as in the normal English letter system. This is our sample variance. So we have s squared, and it is again the sum of our xi, so our data values. Here we have x bar. So my bar got a little long here. Remembering that x bar, I'll kind of remind us how we read that, is our sample mean. So we would calculate the sample mean, subtract it from our x's, get all those values, and then we're going to square them. We're going to add them all up, and then we divide by n minus 1. Now, n is our sample size. Okay, so we're going to take 1 less than our sample size. And the reason we divide by n minus 1 instead of n is we would rather overestimate our variance, how variable our data is. A lot of times when you take a sample, as we kind of talked in chapter 1, we can get some biases happening by those people that like to be in samples, like the ones who like to return these surveys, or the ones that have extreme opinions one way or another. So to kind of make it seem less, or maybe a little bit more variable, because we aren't getting the big picture, we will divide by something a little bit smaller. So we're going to be a little bit large on our variance, but we'd rather be large on our variance than too small. And that's the one reason we divide by n minus 1. There's been lots of studies on it as why we don't do n minus 2 or n minus 3. And n minus 1 seems to work really, really well. So now if we wanted to calculate our standard deviation, which is the true measurement of spread, statistically speaking, we would, again, we're going to do the population standard deviation or the sample standard deviation. Basically, what we are going to do is take our square roots of these values. So we will have sigma, which is that funny little Greek letter, is the square root of sigma squared, or the square root of that formula that we had above. Or if we're doing a sample, that's s, it's just going to be our square root of s squared, and that would be the square root of that ugly formula up above. So I'm going to go through an example by hand. I will show you how to do this in Excel and again on StatCrunch rather quickly, because we have seen it in StatCrunch on our previous video for 3.1. And the steps for it in Excel are very similar as well, but I will go through it in this video so you can at least see it. But I do want to go through it by hand, just so that you can, first of all, appreciate the fact that we don't have to do it by hand. And second of all, to kind of get a feeling for the formula itself and what it is telling us. So here is my data. So the first thing before I go and do my standard deviation and all that, we'll calculate the range. The range is something very simple to calculate because it is our largest value. And I do have these in order. So 17 minus our smallest value of 4, which is 13. So that tells us that we will range 13 units. I don't know. So it's a little bit spread out. Well, if we were comparing it to a different range of, say, 5,000, we know that our range is smaller, spread over a smaller range. Okay, but let's go and calculate our standard deviation. And to do that, I'm going to be going through that variance. And for this example, let's assume this is a sample and not a population. The only difference is in what we will divide by. Okay, so the first thing I need to calculate is my sample average. So I do need to calculate X bar. And if we're doing it by hand, that means we're going to add up our data values. And we're going to divide by the number of data points that we have. And my calculator is right here. So I'm going to add my 4 plus my 7 plus my 13 plus my 17, and I get 41. Divide that by 4, and I get 10.25. Okay, and I am going to kind of work vertically with these. So I'm going to list my data here. And so there's my original data. So these are like my little XI pieces. So these are my little X's. And the first thing my formula tells me to do is to take my X value and subtract off the mean. So I'm going to take my Xi, I'm going to subtract off that X bar. So that means I'm going to take 4 and I'm going to subtract off 10.25. I'm going to do 7 minus 10.25. I'm going to do 3 minus 13, sorry, minus 10.25. And 17 minus 10.25. And I'm going to get these values. So if I take 4 minus 10.25, I come up with a negative 6.25. If I do this subtraction, I get a negative 3.25. Here I get 2.75. If I do this subtracting, I would get 6.75. Okay, these things do have a name. They're sometimes referred to as the deviance. Sorry, I didn't spell that right. The deviance. It's telling us how far our data value deviates from the mean or differs from the mean. So for example, this 4 is 6.25 units, and since it's negative, smaller than our mean. The 7 is 3.25 units smaller than the mean. 13, since this is a positive, is 2.75 units larger than the mean. So these are the values are called deviance, how far these things differ from the mean. What the standard deviation kind of does for us is it's an average of these values, so to speak. Average means we would add them up and divide by however many we have. However, if I add up my deviance, because the way we calculate the mean, we're going to have just as many above as we do below. So the sum of our deviance, if I added these up, they will always add to 0 because some were smaller and some were larger. So what we do with them is we're going to square them. And that, by squaring something, when you take a negative times a negative, it turns into a positive. So that negative piece disappears. So that's why we square those things. So we're going to take those little deviants and we're going to square them. So we're going to take that negative 6.25 and multiply it by itself. And we get 39.0625. We're going to square that 3.25, or that negative 3.25. Square it, and we get 10.5625. We're going to do that to the 2.75 and the 6.75. I'm going to quickly do that. That's a 5, so 7.5625, and then one more. And we get that value. So those are the squares of our deviance. So this is kind of like the inside piece right here. So these little pieces inside. Now we've done all that. The next thing is we work our way out and we're going to add those together. So I'm going to take these four numbers and we're going to add them together. And pray that I don't hit the wrong button on my calculator. Okay, when I add these all together, I have 102.75. Okay, so that is my numerator. That is this piece up on top. And now what we're going to do is we're going to divide this by, so my S squared is this number divided by my N being my sample size, how many data points I had, which was 4, minus 1, which is 3. We're going to divide that number by 3. And that gives me 34.25, kind of a nice value. Doesn't always happen that I get nice values turning out. So this number that I just found, that is my variance. To find my standard deviation, which is one more step, so to find my S, which is the standard deviation, if this were a sample, if this had been the population, I would have just divided by 4. And then I wouldn't have been looking for S squared. We would have been actually trying to find sigma squared. But most of the time we are dealing with samples. So most of the time you'll be dividing by the N minus 1. So to find my standard deviation, we need to take a square root of this number. So 34.25. And so we kind of have to remember how to do that on our calculators. Okay, right now you can see, if I can get the glare not to be there, I have a 34.25 in there, and I want to take the square root of it. My square root button is kind of above my x squared piece, so I need to do a second function, square root, so you'll see the square root in there. I can type in that 34.25. I'm going to close off that parenthesis, although closing it off is not completely needed. The computer knows, or the calculator knows, sometimes I'm a little lazy. And we come up with 5.8. I'll just put a couple digits here. So you can check yourself to make sure you know how to work these. So there is my standard deviation. Okay. And what the standard deviation kind of tells us is how spread out your data. So I believe I wrote it in here. Hope I did. On the next page, I did. So at the very top of the second page of notes, it does tell you that the larger the variance in standard deviation, so the bigger that number is. Now we got 5 point something, the more spread out your data is. The smaller it is, the more tightly compact. So if you were looking at graphs, so to speak, if you have one, you know, that looks like a bar graph that just kind of like, I don't know. So it looks something like that. And that looks kind of all spread out. This one would probably have a somewhat large standard deviation or variance, as opposed to something that was tightly compact and just had, you know, was all smushed together. This one would have a much smaller variance or standard deviation. Okay. And a lot of times we use that measurement to compare one data set to another to say this guy is more compact, more less spread out than this one over here. All right, I do want to go to Excel and StatCrunch to remind us how to do those. So I'm going to stop sharing that screen and we'll go to, let's go to StatCrunch first. Okay, and I did type in the 4 digits or the 4, yeah, our sample size or sample right here, the 4, 7, 13, and 17 into our first column. And I gotta remind you that if we're doing some summary statistics, as this is what that's called, is our summary statistics, we go into stats, and that's in your summary statistics. We choose columns because that is how we entered our data into a column. And I can just kind of hit the default here. Oops, first I have to choose my category, I'm kind of glad that I make these mistakes in these videos because I want to make sure that it's okay to goof up every once in a while, as long as we kind of like, oh yeah, I forgot to do this thing. So make sure you select a column that you want to work with. And here's our summary statistics. There was that 10.25 mean that we came up with. Our variance of 34.35, which is what we had. And our standard deviation, they put out a few more digits than I did, that 5.85235, if we would have rounded a few more. So there are those two pieces of information for us. So again, we went to stats, summary stats, and then column. Okay, I'm going to stop here and I'm going to show you how to do it in Excel. Okay, and I guess I didn't type them in this time, so I'm going to have to type them in. So 4 and 7 and 13 and 17. So there are my 4 values. And we're going to find the variance, just to be on the safe side, and that standard, I'm going to abbreviate here, standard deviation. Okay. Reminder, when we are in Excel, and similar for Google Sheets, they have some functions that are already built into that spreadsheet software. So here we go into this little FX button. And again, we're going to go to the statistical category because it's probably not one that you use all of the time, except I suppose after doing some homework, it may be, but it is in the statistical. We are finding the variance. So that's going to be a V. So we have to scroll down to the V's. Okay. And the one we're going to use is a VAR. So VAR is for variance. Notice they do have a dot P and a dot S. The dot P means we're looking at a population variance, or S would be the sample variance. So we assume that this was a sample. So I'm going to click on that one. Notice it does say here, estimate the variance based on a sample. If you had clicked on this one, it says based on the entire population. So I'm going back to that dot S, hit my OK. I want to have A1 through A4, A1 through A4. You'll notice the 34.25 came up rather quickly. And we'll do the standard deviation just to kind of clean that out. So we're going to go down our list. Standard deviation is STDEV, and again, dot P for population, dot S for sample. And we're going to grab our data. So A1 through A4, and there's that 5.85234, da 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 da. And if it rounds, you can get more digits by making this wider if you wanted to. I just grabbed on the bar between the A and the B and stretched it one way or the other if you wanted to shrink it. So that is, again, reminding us how we find those values in terms of StatCrunch or Excel. I'm going to continue with our discussion in here, and we have a couple more things to talk about, and that is some nice things that happen when we have our data that is bell-shaped or possibly not even bell-shaped. And we'll go through an example as well. So wait for it to click over. And this is our empirical rule. Okay, let's see here. All right, if our data is roughly bell-shaped, so nice and symmetric, high in the middle, bell-shaped, if you can remember what it looks like, we've talked about it a few times. What we have is roughly 68% of our data will lie within one standard deviation from the mean. And I'm going to draw a picture after I go through this. And we will do an example as well. Roughly 95% of our data is going to lie within 2 standard deviations from the mean. That's 2 standard deviations up and 2 standard deviations down. And it turns out that roughly 99.7 of all of our data will lie within 3 standard deviations from our mean. Okay, so picture of what's going on. So I'm just going to draw this as kind of a curve instead of bell bars. So imagine bars kind of lying underneath this curve that is bell-shaped. So bell-shaped, remember, nice and symmetric. Does this might tail on for quite a ways, it might not tail on for a while, but we've got the high hump in the middle and it goes down on either direction. Okay, since it is nice and symmetric and high in the middle, bell-shaped, we know that our mean, our median, and our mode are all in the center. We talked a little bit about that in 3.1. If the mean is skewed to the right or skewed to the left, we don't have this shape. But if we have this nice shape, our mean, median, and mode are going to be all smack dab in the middle. So I'm going to put our mean in here because we were talking about the mean. Okay, what this tells me is if I go 1 standard deviation, which is a value that I calculated. So we go 1 standard deviation up and 1 standard deviation down. So if let's say our standard deviation in that last problem was 5 point something. So if I went 5 point something units above that 10.25 and 5 units below, we will have in here roughly 68% of our data. Okay, now our data wasn't we didn't have very much data, so it's kind of hard to talk about being normally distributed or bell-shaped because we only had 4 data points, so it would have been pretty uniform-ish. Okay, if I go another standard deviation, so this is a standard deviation up. If I go another one, so I'm going 2 up and 2 down. So from here to here, we will pick up 95% of all of our data. Okay, and if I go one more, and I go from here all the way to here, we have just grabbed at least, or right around 99.7% of our data. And we will do an example of what this kind of gives us. And it's okay if this is a little like foggy and doesn't make a whole lot of sense. With the example, hopefully it will. And we will be using this curve a lot more when we get into chapter 7. So this is just kind of a brief introduction to this curve with this empirical rule, this 68, 95, 99.7. So 68%, if I go 1 up, 1 down, I go 2 up, 2 down, we get 95, 3 up, 3 down, 99.7. Provided it's bell-shaped. If it's not bell-shaped, then these numbers don't apply. If it's not bell-shaped, if you go K standard deviations, whether it be 1.3, 1.5, 2 standard deviations, whatever that number is, as long as it's bigger than 1, we will have this percentage within that region. Okay, and this is Chebyshev. It's oh shoot, I want to say it is actually starts with a TS. but a lot of people have changed his spelling to Chebyshev's. I want to say it's Russian, but I'm probably going to be wrong. So, but it does usually start with a TSCH, which is kind of weird. But anyway, I'll do one of these here in this next example so we kind of can see the difference between the two. All right, so let's just suppose, here's our example to kind of work with that empirical rule a little bit and to also see Chebyshev's inequality, this little guy in action as well. So let's suppose we have some soda cans and they have a diameter of 92 millimeters. And let's say an average, I should put in there, an average diameter of 92 millimeters with a standard deviation of 0.3. So we've got this machine that makes these soda cans, and they took a bunch of them, added them together, found out that an average of 92 and standard deviation, they did the calculations and they got that to be a 0.3. And we have some questions. And let's say if this data were bell-shaped. Okay, so we can kind of look at it. Bell-shaped means, all right, so here's our bell. Drawing my little bell. Okay, since it is bell-shaped, that 92 is going to be smack dab in the middle. Okay, and I want to know what percent lie between 91.7 and 92.3. Well, it just happens that they took this 0.3 and they went up 0.3. That gives me that 92.3. And they went down to 0.3. So we went one standard deviation up and one standard deviation down. So by the empirical rule, we're going to have that 68%. So we're going that 0.3 up and that 0.3 down. So we get that 68%. Just to kind of lead us into the next pieces, let's get those other kind of boundary values that the empirical rule works with. So going another 0.3 up, that's going to give me 92.6. That would be 2 up. If I go 3 up, that's going to be 92.9. If I go another 0.3 down, that takes me down to 91.4 and then 91.1. Okay, so 68%, 95%, 99.7%. Keep those numbers in mind. So I want to know what percent went between 92 and 92.3. Okay, now remember we had 68 from here to here. This is bell-shaped, which is also symmetric, even though my picture doesn't show it. So symmetric means it's going to be even on both sides. So it should have looked like a mirror image on this side, mirror image on that side. So it is actually that 68% divided by 2, or 34%. So half of that 68. Because it is nice and symmetric, what we see up here, we're going to see down here. All right, the next one says, what is it? Where would the middle 99.7 of the cans be between? So 99.7, that's that magic third. So 3 up and 3 down. And we already did that. So that would be between 91.1, which is 3 down, 3 times 0.03 or 0.3 to 92.9. 3 standard deviations up, 3 standard deviations down. Right, this one's a little tougher. What percent of the cans will be between 91.1 and 92.6? So it's not 3 up and 3 down, but it's 3 down and only 2 up. Okay, so we're going to have to play with it a little bit. And the way we can do that is, again, remember that symmetry. So if I went 3 down and 3 up, that's the 99.7, but we only have half of that. That'll give me this piece here. So I'm going to take that 99.7 and divide that by 2. That would fill in that region there. But I still need to go all the way to 92.6, which is half of the 2 up and 2 down. So half of the 95. So I'm going to go 99.7, divide that by 2. That gives me the 49.85. Adding my 47.5. And I have 97.35. So most of our cans are going to be within that region. 97.35% of our cans that come off this machine will have a diameter somewhere between 91.1 and 92.6. Okay. Now, what happens if it's not bell-shaped? Then all that 68, 95, 99.7 stuff went out the window. Okay, but I am going to kind of look at it and say, okay, if we don't have bell-shaped, and I was still going between the 91.4 and the 92.6. If it was bell-shaped, we'd have 95%. Okay, if it's not bell-shaped, we can't apply the empirical rule. So we have to go with Chebyshev. Okay, so in this case, we went 2 standard deviations up, 2 standard deviations down. So 2 standard deviations from the mean. Okay, I should have just said, so 2 up and 2 down. For Chebyshev, we have to maintain the equality on both sides because we don't necessarily have that symmetry. Like here, we could split and look at half, but that's because we have the symmetry. When we're dealing with something that's not bell-shaped, we have no idea what the shape of the information looks like. So we can't split it and go 2 up and 3 down or something like that. We have to maintain the 2 up and 2 down, or 1 up and 1 down, and 1.5 up and 1.5 down. So we're going 2 standard deviations up, 2 standard deviations down. And I chose those just to make it easy for us to see. K represents how many standard deviations we went up or down. So in this case, K is equal to 2. So our formula from Chebyshev says we have 1 minus 1 over K squared times 100%. This is going to be 1 over 2 squared is 4. The 1 minus a fourth is 3/4. And 3/4 in its decimal form is 0.75. So that means we'd have 75% of our data. Okay, if it were bell-shaped, that's going to push everything towards the middle. So that's where we can get more information, or get more in that middle, that jump, and notice it tailed off to the ends. If we have no idea what the shape is, it could be U-shaped. So it'd be high on the ends and low in the middle. Chebyshev still says we're going to get at least 75% of our data in that region. Okay, this is not something that I concentrate a whole lot on, but you will see a few problems in the homework on it, as well as possibly the project, but I do not believe I put anything on the quiz for it. But I'm going to stop sharing. And that kind of concludes 3.2. Our next section looks at what happens if we have grouped data. So let's say we have a frequency table. Someone lost the original data, so we have it all grouped in classes. How do we get a hold of what the average is? How do we find the standard deviation? Because we don't have the normal data anymore. So we're going to look at how we talk about that. But that's in the next video. So I am going to stop here, and I will tell you to see you in the next video.